I need fingers. Like, I think it's
All right. Well, I'm getting started now. Happy Halloween, and I'm glad that not too many people spend too much money on stuff. My daughter just bought a makeup kit yesterday. So I know how it can be expensive, can be inexpensive depending what you're getting and where you get it, stuff like that. I would just go to my my little tar pit in the backyard and just get something. Then it'll smell like that too. Tar pit. All right. So what we'll do today is we are going to write the binary search algorithm today. And we'll go ahead and start with the homework assignment. This is a new homework assignment. I'm going to talk about the other one first, to give you the solution to that one. But we have a new homework assignment. Unlike the other homework assignments that you have done so far, this one actually has an quote-unquote expected behavior, but it may not do that. Okay, so it's your job to find out, hey, this algorithm is not doing what it is supposed to. But you have to detect that condition and then let me know and say, why do you think it is not doing what it is supposed to? Okay, so we'll go back to the previous topic. I changed the layout of Moodle a little bit. I think it's easier to navigate this way. Some people may not like it this way. How about you guys?
It did it right when I was in the middle of it, so I got some funky error. It's kind of crazy.
Okay, so this is the homework that was due about 3 minutes ago. And we'll go ahead and take a look at this one. This one is, I did not intend it to be tricky, but from the questions that people ask, I can see that there's one place that can be just a little bit tricky, not too much. So I'm not going to take too many points off, because of that one little part. Okay, this is the algorithm. I made a change to it, and I sent an email to everybody. So I hope nobody used the original version of this file, for the homework assignment.
I did.
You didn't?
I did.
You did?
I did.
Oh, okay. If you use the original one, if it's consistent with the code from that particular version, it will still be okay. Because I know it's faulty, but it still has a certain behavior. So as long as the trace is consistent with that one, it will still be okay. But the question is, why are you not getting my email?
I don't think I have my
Gmail?
Yeah, my Gmail forwarded to my family email.
Oh, okay. So you might want to. Okay, so you might want to set it up to make sure that you get all the forward, because that's how I will kind of keep in touch with you. It's also how D2L and the other systems will also use to communicate with you.
I had iMail forwarded to it, and then they switched over to the Gmail.
To apps, yeah.
Well, and even in the beginning of Gmail, I had it forwarding, and then it stopped after a while. So yeah.
Yeah, it did for me too.
And then I had to go in and forward it again. When it was
Really? So they changed something.
Yeah.
Okay, well that part unfortunately is out of my control.
Well, this was at the beginning of the semester.
Right.
Maybe it was the other semester.
All right, so what we'll do is we'll go ahead and trace this particular algorithm in sheet 2. You have to use this as a starting point. There's no other way to do it, because you have to know the content in the array before you can start to trace in this particular one. All right, so let me resize this one, display the other sheet, and just magnify as much as I can in order to perform the trace. I think I might have mentioned this. This algorithm actually is meaningful in a way, because it is one step of the bubble sort algorithm. Okay, it's not the entire thing. You can see that the array is not completely sorted when it's all done, but it is one of the steps of bubble sort. Okay, so we'll go ahead and get started here. Line 1 initializes I to 0. So let me just kind of save some space here, because I think it will take up a little bit more. We'll start with narrow columns until we need to make them a little bit wider. Then we move on to line 2. Line 2 has to evaluate this expression. I is less than bar a bar minus 1. And somebody came see me and said, Heck, I'm so glad that I watched your video, because at first I thought bar a bar means the absolute value. And how do you take the absolute value of an array? Well, it's measuring the number of elements in an array. That's what bar a bar means in the context of this class. Okay, So we have to count the number of elements in A, which in this case is 4. 4 minus 1 is 3. I has a value of 0 at this point. 0 is less than 3 is true. Okay. So we move on into the loop. We go to line 3. We evaluate this condition here, which seems a little bit, complicated. But what it really is doing is to compare A bracket 0 to A bracket 1, because I has a value of 0 at this point. Are we doing okay so far with that?
Yes.
Okay. It is important to keep the +1 inside the square bracket, evaluate the entire I plus 1, and then use it to tell you which element we are accessing, and not put the +1 outside of the square bracket, which is sometimes what people do. Okay, A bracket 0 has a value of 4, A bracket 1 has a value of 6. 4 is greater than 6 is false, so we skip around the entire conditional statement. We get to line 8. Line 8 is adding 1 to I goes from 0 to 1. Get back onto line 2. I is now 1. 1 is less than bar A bar minus 1, which is 3, is true. Go to line 3 again. A bracket I this time is A bracket 1 because I has a value of 1. So this has a value of 6. A bracket I plus 1 is referring to A bracket 2, which at this point has a value of 2. 6 is greater than 2 is true. Okay. So we have to get into the conditional statement on line 4. Line 4 is picking up, copying the value of A bracket I into T. A bracket I is A bracket 1, has a value of 6, so now T has a value of 6. We move on to line 5. Line 5 is an assignment statement. Even though we have an array element on both sides, it's no big deal, okay? Because on one side we're just evaluating. Okay, do you guys have any questions in the back? Okay, so could you please focus? Okay, thank you. All right, so even though we have an array reference on both sides of the left arrow, it's okay because we just have to evaluate the right-hand side first and see what kind of a value we come up with. The right-hand side is A bracket I plus 1. I at this point has a value of 1. I plus 1 is 2, so it's referring to A bracket 2. A bracket 2 currently has a value of 2, so the right-hand side evaluates to 2. The left-hand side is A bracket I. I has a value of 1, so A bracket I is A bracket 1, which is referring to column F. So that's why column F is updated now to a value of 2. And then we go to line 6. Line 6 is actually easier because now we only have T on the right-hand side. T has a value of 6. The left-hand side is A bracket I plus 1, which is the same as A bracket 2 because I has a value of 1. So now column G is updated to a value of 6. Then we are done with the branch. We get out of the conditional statement. We continue on to line 8. We add 1 to I. It goes from 1 to 2. And then we go back to line 2. Are there any questions at this point? The second iteration is not really the tricky one. The tricky one is the third iteration, and I'll show you why the third one is the tricky one. Okay, so here we have the condition again. I is less than bar A bar minus 1. It's still true because I has a value of 2. Bar A bar is 4. 4 minus 1 is 3. So it is still true that this comparison is holding true. We move on to line 3. This is really the tricky part. A bracket I is not the tricky one, okay? Because what is A bracket I? It is I has a value of 2, so we are referring to A bracket 2. The question now is what is the value of A bracket 2?
6.
It is now 6. It is not 2, okay?
This is the reason for an array, correct? Because this is the reason for an array, correct?
This is a reason for.
This is the purpose. Yeah, this is the
Yes.
benefit of having an array is to be able to update.
Right, and also.
Continually rely on, like, where we're talking about the GPA. How do you find out who's got the highest GPA? You
Right.
continually update with the higher GPA until it reaches the end.
It's not exactly the advantage of an array in this case. It's just that this algorithm would push the largest value to the end of the entire array. It's called bubble sort, but it's actually it's actually quote sinking the largest value to the bottom in this case. Okay, and so we have 6 as A bracket I, And then a bracket I plus 1 is a bracket 3, which has a value of 5. 6 is greater than 5 is true. Okay, this is probably the trickiest part of this entire trace is this part. Because if the condition is evaluated to false, then then those people will miss the third iteration and not do the swap in the third iteration. Okay, we move on to line 4. We already kind of know what it's going to do. It's going to take the value of a bracket 2 in this case into t.
It's 6.
So, oh, it's 6. Yep, it is updated to 6. That's why you have to look here. And then we move on to line 5. It puts the value of a bracket I plus 1 to a bracket I. That would be 5. So we update a bracket 2 to a value of 5. And then on line 6, we copy the value 6 to a bracket 3. So it goes like this. And then once we're done with line 6, we are done with the conditional statement. We get out to line 8. We add one to I. It goes from 2 to 3. We go back to line 2. The condition will fail this time because I is now 3. 3 is less than 3 is false. We get out. We get to post, and we're all done. Yep.
For line 16 of the spreadsheet, we need to update it to 6 right there.
It is officially an update. If you don't show it, I'm not gonna take any points off because it had a value of 6 already. But I prefer to put it there, just so that we understand that there's an assignment statement on row 16 of the trace, and it is, putting a value of 6 into the variable, even though it had a value of 6 already. Yep.
Where are you giving a 6, like the column 6?
Say again?
In the G. Where are you giving
On line 6.
No,
You mean, are you referring to this row?
oh yeah.
So it is line 6 that is doing it because it's copying from T to a bracket I plus 1. And at that point, I has a value of 1. So a bracket I plus 1 is a bracket 2. And that's why column G is updated to a value of 6.
Okay, so the plus 1 is on the outside of the bracket, it changes what?
It changes because if the plus 1 is inside the square bracket, you have to compute I plus 1 before you use the bracket notation to find out which element you're referring to. If the plus 1 is outside of the square bracket, then you get the element first, and then you add 1 to the value of the element. So that's why the order is important. And that's also why we kind of talk about that tree, the reverse tree thing. Okay, so we know how to break down an expression into its individual components and understand the ordering of which part to evaluate first. Okay, so that's basically the answer of this particular homework assignment. And I think most people get the first and the second iteration. It's the third iteration that some people would have missed, something. And I'm not going to take too many points off, because of the third iteration, because the second iteration will clearly indicate that people understand how to access an array. But the third iteration shows me that whether people can read the trace itself correctly and use the most up-to-date value of a variable. So it is still important, but it's not like the entire thing, in this assignment. All right. Any questions about this particular homework? Roll sheet. All right. Okay. I know today is Halloween, but I will still kind of be. It'll be nice if people don't leave just a blood stain on this roll sheet today. So I'm gonna sign by my finger and go like that.
Can you leave this up for just a little while longer?
Sure.
Eventually you'll have a roll sheet that we spin into.
Yeah. It's just a device, you just pass it to the next person like that. Yeah. And then in Gattaca, somebody will sign in for somebody else by having a little vial, right? Drop.
They'll knock you out and scrape the inside of your mouth.
Yeah. Yep.
Are we going to get our exams back?
Yes, I actually have it here. I have had it with me last time too. I just forgot to, pass it back to the entire class. This is actually the only time I get to Well, this is the only opportunity that I can actually get to know who is who, put a face to the name. Some people I know, but most people I do not, because, it's a pretty big class, and, I normally do not take role by, calling people's names. So I'm going to do that this time, just so that I can put a face to each name. Yeah, I'm gonna butcher first names and or last names. First name is Levon, Levon. There's no score on the exam itself, so don't worry. If your neighbor sees, your exam,
just right off the bat.
just nothing on it. Everything is on Moodle. Okay. Alex Warren. Certain names I can pronounce. Ming Yang. Pedro.
I screwed up my additional assignments. So
Richard
T
Cole.
became 4 instead of T became 6, and I went through the whole thing with 4 instead of 6.
Sean Austin.
Thank you, I am.
Sean Austin. I think that person dropped the class already. Jeffrey Burns. Mac Hill.
Well, at least it'll get me partial.
Mickey. That's good exercise for me.
At least it wasn't the array card that I told it was just the stupid.
M-O-N-A Mona. On here, Christian. First name is Christian. Daryl. Daryl Gill. Kevin Dunn. Dennis. Richie Lee. Kevin Bang. Taylor Ashby. Miranda. I think it's Kyle. Kyle Casey. Dylan. Okay. Don't worry. This one is Lewis. L-U-I-S. Okay. Christina Quintos. Christina Quintos. Go. Tommy Faye. Ahmed. Viet. Philip. It's not here. Timothy Marvin. Next one is Nehemya is the first name. Andrew M. Ahmed. Okay. Go. I think next time we'll ask you guys to bring a little picture of yourself, and then we'll just kind of stick it on the exam. John T. Last name. Timothy Jeffrey. Jeffrey? Timothy Jeffrey. Nope. Or Jeffrey Timothy. No. Seth. First name is Seth, S-E-T-H. First name is Caleb, K-A-L-E-B. Caleb. Okay. Adam. First name is Adam. This one is Victor. Victor K. Devin, D-E-V-I-N. Richard. Okay. Becca, Chester. Over here. Michelle Thomas.
Okay.
Yeah. Kevin S. Ellis.
Here.
Ellis Berry.
Here.
Oh, sorry. Tim Lerman. Trying to find the best way to get to you. There you go. Zachary.
Yep.
Nod.
Thank you.
All right, this one is going to be a challenge. Jen.
Eugene. Eugene.
No, let him do it.
You're gonna force him to try? That's so cruel.
And the last name. No, read it. And
What was the time and test?
class average is actually really good for both classes, the morning class and also the evening class. Did really well. Okay, so I think you guys know your ranking. You know, if you look up your grade book, you actually can see your own ranking. What I'll do is I'm gonna switch the screen to a different source so I can, do something here, and then I can show you a spreadsheet of, the school overall, performance of the class. Go ahead.
So if it says you're like number 5 out of 47, that means like you're like.
Your rank number 5.
That's kind of cool.
I don't know where you can find. I didn't see the ranking. Can you
It's
do
right
it on
next to the
mobile?
grade.
What's that?
It's right next to the grade on Moodle. It says like 1 out of 47 or 5 out of 47.
Yeah. So let me switch to
one
it.
that says 47 out of 47.
Let me switch to a different screen so I can show
Oh, there's
you.
only 47 now.
I know.
American one photo.
What is it?
American one photo.
Oh. That's amazing.
Okay, I'm almost to the point where I can, show you the display again. Just have to get out of this screen and do something about this here. Go. Okay. All right, so let me show you the screen again. All right, so this is a column A is the sorted column for all the grades for the first exam. And you can see, okay, let's go from the best scores and then go back up. There are, 8 people getting perfect scores. So 8 people amounts to, I think, 43 or so, have, 100% out of 100%. And then we have a whole bunch of people getting really good scores. I mean, everything, let's see, 87.5% is an A already. So 87.5% translates to what in 20? 87.5 times 2. Okay, what is that?
That was 17 something, 17.5.
17.5? Okay. So basically everybody in this range are officially getting A's too. Okay. So out of the entire class, we have everybody going from here to here getting A's. And I think that's about what? About half the class already, kind of right there. So overall speaking, as a class, I really think that the class, did well in this test. And then if I scroll up, then we have the rest of the class. I think the other way to look at this is like this. Okay, so let me pick the other way to show this. We'll go ahead and insert object chart. That's the other way to look at it. I mean, this is really, really easy to look at. Because a B is centering around 15, so you basically look at the line of 15 here. You go halfway up and halfway down. That would be the range of B's. So we have some people getting B's, but I would say people getting B's are actually, compared to A's, is the minority. The majority is getting A's. Then we have some people getting B's. Centering around the 10, halfway down, from 10 to midway between 10 and 5, 7.5, and halfway up would be people getting C's. Okay, that would be the C range. So the C range, if I just kind of eyeball this, has 1, 2, 3, 4. About 4 people are getting C's, excuse me, and then the rest would be getting D's. D's would be arranged would be around 5. So we have, I would say, just eyeballing this, we have 1, 2, 3, 4, 5, maybe 5 people getting D's, and then about 3 people getting F's. So I would say it's definitely skewing, way over to the A's in this particular exam. Okay, is that helpful? I mean, just looking at the picture. Yep.
So on like the Moodle and stuff, are all 8 of those people going to have a 1 out of 47?
Yes. Yeah. So everybody who get 20 out of 20 will get a ranking of 1 over the number of people in class, and whoever is getting the next score will automatically be 9 out of the number of people in class. For all practical considerations, 19.5 is 20. I mean, it's basically so close that it doesn't really matter. Even though the ranking, it's like, oh, I'm 8 down, from the top of the list. No, it's not that important. Okay, and in this class, I'm only grading, I'm assigning letter grades, in an absolute fashion, which means I'm not grading by curve. Okay, I'm not saying only the top 5% of people can get A's in this class. Okay, if everybody can meet that expectation, everybody in this class can get A's, which is more than what I can say about other universities and also other professors. Okay, when you get to Berkeley, for instance, many of those classes are graded by curve. Is anyone familiar with the concept of grade by curve? What does that mean?
Cutthroat.
Cutthroat.
Yeah, cutthroat.
Well, it's just, the highest scores.
They have
balances
percentages.
out, yeah.
Yep. They have basically allowances, right? We can look at it as allowances. Yep.
Means you don't want to help anybody else with their homework.
Pretty much, because if you help a fellow student, that means that fellow student may score better than you in the exam, and therefore bump your grade down to the next level, which I think it's a different culture. I just do not agree with that kind of a culture, and I think just if everybody can help out everybody else genuinely and improve the score, and the understanding of the material, hey, why not? And I don't have any problems with that. But that's just the way I, assign grades in this class. Yep.
I've had them where they don't count like the top 3, bottom 3 or something, but it's really helpful when you have a crappy teacher, because if everyone's doing bad.
Well, if everyone is doing bad, if the skew is on the lower side, I typically will do something about the grade. I would do some adjustments to the point values. Sometimes it happens to my other classes like cisp300, or there's a new class I'm teaching. Sometimes I would have exams that are just a little bit too hard. and I would make adjustments for that. Yep. But typically for a class like this, which I have taught many, many years, I just, kind of know what the curve is supposed to look like. Okay. Any questions about the distribution of grades in this class? No questions? Okay, all right. So I'm gonna put this out of the way. We are done with the homework assignment due today, so now it's time to move on to the homework assignment that's due next Thursday. All right, so next Thursday we have Array 2 as a homework assignment, and the description is almost exactly the same as the one before, except for certain places. The certain places that are different is you have to look at sheet 2, 3, and 4. Okay, so there are 3 traces you have to do for this particular homework assignment. It's not going to be long. Okay, it's not designed to be really long and time consuming. It is just just to make sure that you understand the algorithm and start to understand why the algorithm is failing. Okay, so we'll go over the algorithm today, the correct version, but this is an incorrect version. It does not work the way it is supposed to. And also, this part is also new. If you think the trace will not end, indicate so and explain why you think so. Okay, just don't tell me that it's not going to end. You have to tell me why it is not going to end in your own words. Okay. So we'll take a quick look at the algorithm itself. This is the algorithm. It is almost correct. It's not entirely correct. It's just almost correct. You have sheet 2 as one starting point, 3 as a starting point, and sheet 4 as the other starting point. So 2, 3, and 4 are starting points, and you can see the only thing that changes is column F. Okay, so you're searching for a different value in these 3 test cases, and you have to tell me, is it going to finish? If it's not going to finish, why do you think it is not going to finish? Okay. So that's your homework assignment. I suggest that you get started early. So if you have any questions, you can ask those questions on Tuesday, because the assignment is due on Thursday as usual. 1 week of time for you guys to do the homework. All right. So now that we are done with this part here, it is time to go ahead and try to write the algorithm itself. Okay? We're going to write the binary search algorithm. Last time we talked about a lot of stuff that won't be in exam 2 or the final exam. Okay, the whole thing about the programming competition between Pat and myself, at a company, because it's downsizing. We need to figure out who to let go, and then we have the UPS problem. Okay, the program worked fine for pizza delivery, and somehow it doesn't work. When we try to run the same algorithm for package delivery. And by the way, I got a UPS package yesterday, so I took the opportunity and asked the driver how many stops, is typical for a UPS truck. And he said, on a light day it's about 180, and then yesterday was kind of a hefty day, so he had about 220 stops. So we are talking about 200 factorial, which is a huge number. Okay? Yeah, because last time I think we looked at 100 factorial is already 40 factorial. Okay, so 100 factorial is an insanely big number, because, well, since I have the spreadsheet up here, I'm just going to borrow a part of this to do this calculation here. So we're looking at a factorial of 200, and it says cannot deal with it. It's too big for the representation. It's too big for the number representation in this particular spreadsheet program.
So it would be a number value.
Sorry?
No.
It's just a huge number. It's not possible to run the algorithm on a problem that big. Yep.
So what do they do then?
What they do is they do localized optimization. You mentioned that earlier.
There was a PBS show about technology. They said that they break it down into time frames and delivery localization, so that they can decrease it down to like 5 stops, and then they optimize that, and then they optimize the next 5, the next 5. I have to break it down. That's
so it's not
it becomes more optimal, because if by time, because they have a time constraint,
Wow.
then they still have to
Break it down
that.
before.
What are the chances that I find this as the first link? That really is the art of putting in the right keywords when you do a Google search. Okay, did you guys saw what I put in? UPS, PBS, and algorithm. Only those 3 words. Okay, and it pops up as the first thing, because those are the most differentiating words that are unlikely to combine in other contexts. And that's right. I mean, yeah. So that's why it pops up like the first thing, and I think it's a pretty long thing. I'm not gonna click it and watch it now. But if you guys are interested, it's probably an interesting read given what we have talked about in this class. So you guys have just about enough material to start to understand what they're talking about. It's a trade secret, by the way. I mean, they're not going to give you the entire algorithm, so FedEx can just copy that and go, yeah, we can just copy that. But it's interesting, how technology and computer science and mathematics, play an important role in the corporate world. Okay.
Actually, UPS was the first business to do the optimizations, and my understanding is that they moved it into a separate division and then made it nonprofit so that they could start to share some of the information so that other companies could do it too, because it's huge savings.
Yep.
But they still want the optimum deliveries because it's still competition within the companies.
Yep. And for those of you who want to know, some other types of optimization, this one is kind of fun. It's not computer science or algorithmic or even mathematical. It is much more empirical than anything else. You want to look up Mythbusters delivery left turns or right turns.
Right turns.
And here we have it. Yep. Left-hand turn. Yep. There we go.
Oh, go back. There's a YouTube video.
Oh, you guys want the YouTube, eh?
We'll learn visually.
Yeah, there we go. So this one is much more empirical compared to the other approach. Basically, somebody sends them a request and say, is it true that if you avoid left turns, even though if you have to circle around the entire block, it's going to save time and fuel for a truck? Okay, and they found that it is true for trucks, but not so true for sedans and smaller cars, because smaller cars can idle and not really consume a lot of fuel. But when you have a delivery truck, it does consume enough fuel that waiting for a left turn can make the difference between can save you fuel at least.
Wow.
And I think it saved time too in the case. So you might want to watch that one too, but it's not scientific in the sense that they did not run a mathematical model to predict what should be done to save fuel. Yep, go ahead.
A good point on that is the trucks we use at work, big like 7-liter diesels. They use the same amount of fuel whether you're idling or you're going 65 on the freeway. Just because
Really?
the engine's range is so short.
Oh, interesting. Whereas with my hybrid, when I'm stopped, it just stops the engine. You just roll down the windows. Yep.
I used to turn my car off every time I'd be stopped, and then I dated this guy, and he was just like, you realize that by turning your car off and then starting your car again, you're using more fuel to start your car again than just when you're idling.
I don't think that is necessarily true.
It's hard on the battery though. It's hard on the battery.
It is hard on the battery because it is hard on any type of lead acid battery. If you want to do it that way, you have to get what they call a deep discharge battery that is actually designed to have deeper discharge than a normal car battery. A normal car battery is designed only for starting, and then you have the entire trip, 15 minutes, half an hour, to charge it back up. It is designed to work like that. But if you stop at every turn, when you have to wait for the light to turn green, then you'll be starting your car a lot more often than you're charging it. And it's really hard on a normal car battery because it's not really designed to charge or take up a charge that rapidly. So you would be draining the battery a lot faster than otherwise.
I didn't mean every time I told him to stop light. I meant like if I was gonna wait out in the parking lot for someone to get in class for 5 minutes, I would turn off my car.
Yeah, that makes sense.
But then idling it for 5 minutes, you're using less gas than you are turning
Yeah, most cars will consume maybe 0.6 to 0.7 gallons per hour when it's just idling. So it's not really an awfully lot of fuel, but it does add up. Yeah. And don't ask me why I have those numbers. Okay, so interesting things, that I think, given what we have talked about in this class, those are things that you guys can kind of look into because it's really interesting. I think it's interesting, and it kind of gives you an idea of the context of computer science and programming in today's world. I mean, it's really not, something, it's not like, oh, we just want to write an application like Microsoft Word or Excel or something like that. It has a lot more applications now than, before. All right, so what we'll do today, right now, is I'm going to give you an example of, binary search, and I'm going to use a spreadsheet to demonstrate, binary search, just so that we can do it by hand a few times before we try to do it, using an algorithm. So in this class, I'm going to give you some numbers. And I think I might have a few repeated numbers, which is okay. And I will have to sort it first, so I'm going to cheat by using the spreadsheet program to do the sorting. It's all done, nice and quick. All right, and I have a few repeated numbers, which is okay. I mean, binary search works really well, whether you have repeating numbers or not. But in this case, I think I might have a little bit too many repeating numbers, so I'm going to change some of these to non-repeating numbers, just so that it's a little bit more interesting, like that. And resort it. Okay, now it's all sorted, and we don't have too many repeating numbers, just 2 5s in this case. Okay, so what I'll do is I'm going to copy this into multiple sheets because we're going to try it several times just so that we understand the algorithm a little bit better. This is also something that you should do too. If you are asked to write an algorithm in your cisp300 class or other programming classes, instead of relying on one single example to show you, how it should be done, you should be running, through multiple scenarios just so that you are prepared to handle different cases by hand, and then you can translate, that logic into the algorithm itself. Okay. All right. So now we will go ahead and say, give me a number that we want to search in this array. It can be a decimal number. In other words, if you think, oh, I think 2.5 would be a tricky one, we can search for 2.5, no problem. 0.9. Okay, somebody wants to look for 0.9, so we'll go ahead. This is a nice, interesting case because it shows how we eliminate possible choices, in a way that is just, it's going to move in one single direction. Okay, so let me just kind of shrink this column first. Okay. Binary search says, given a pile of cards, okay, given an array of items that can still contain the value that we have not confirmed that it cannot contain the value, we'll start from the middle. Okay, we'll pick whatever is right in the middle of the entire bunch and compare. So in this case, we have 15 elements in the array. Which one should I compare to first? It'll be the one in the middle, so which one is actually in the middle? No, it's actually the 8. Okay, the 8 is right in the middle. So we'll compare to this one first. And the comparison result is pretty clear. Okay, 9 is greater than 0.9. Okay, so that's not surprising. The question now is, from only this comparison, I can now say, oh, if 9 is greater than 0.9, the next item is going to be greater than 0.9 too, because the array is already sorted. So the next item is at least as large as this particular item. Given this, which part of the array can I throw away at this point? The bottom half. The bottom half. Okay. So we'll go ahead and say, okay, we cannot use this half anymore. I'm going to use a color highlight to indicate this half is now quote unquote eliminated. And I would use another color to basically say, well, it can still be in this half here because we don't know what is in that half. So it can still be there. We have to test a little bit more to find out whether it is in that half or not. So the green half is basically saying the value 0.9 can still be there. Okay, the red half is saying cannot be there. We don't have to search anymore within that portion of the array. Is that making any sense so far? Okay. So given that we have 1, 2, 3, 4, 5, 6, 7 values left, or 7 elements left, which one should I compare to next?
The half of that.
Okay.
4.
Okay. This one. Well, the one at row 4, which has a value of 5. Okay. So we compare 0.9 to that thing, and we establish that 5 is greater than 0.9. So I can apply the same logic again, right? This time I can say, well, everything from this element and down cannot possibly have the value that I'm looking for, because they're all going to be greater than 0.9. So this half is going to have, the same highlight. I think I picked salmon. Was it salmon? Yep, it is. It was. Okay, and then this portion, which is now much smaller, can still contain the value that we're looking for. Is that making any sense? Yep, go ahead.
If line 3's value also equaled 5, would you go from line 3 or would you still go from line 4?
Say again?
If the value in column A for line 3 was also 5, would you go from line 3 or would you just still go from line 4?
It will still go for line 4, because line 4 is picking the element based on its position in the array, not its value.
All right.
And in which way we throw away, is determined by the comparison itself. Okay. Now we have three elements left. Which one is the middle one to compare to? The one on row 2. All right. So row 2 has a value of 3, which is also greater than 0.9. And now we have the conclusion of, hey, we are eliminating all but one of these, elements. And I think salmon. And now we have only one element left. Now with one element left, we're not done yet. Okay. At this point, we cannot conclude and say 0.9 is not in the array, because we got one element that can still be the value 0.9. So this is our last comparison, and say that the value 2 is also greater than 0.9, and at this point we can say, okay, well, we cannot possibly have the value 0.9 in the array because we have just eliminated everything. There's nothing green left on column E, and as a result we can now make a conclusion and say, okay, 0.9 is not in the array. Yep, go ahead.
If it were, say, 2.5, then you'd get 2.5 is greater than 2, but how do you just say it's not in the array still?
That's why we got sheet 2, 3, 4, and 5. Okay, let's pick another tricky one. Okay, how about 7.1? Would that be kind of tricky? It's kind of like in the middle. So how do we zero in and yet be able to rule out all the possibilities? Would that be okay? 7.1? Okay. All right, so we'll try 7.1 in this case. Okay, so we are looking for the value 7.1. But this is how you kind of analyze the problem, right? I mean, you don't just use values at the extremes, okay? Once we know the behavior of 0.9, you're looking for 0.9, which is smaller than the smallest value of the entire array. Trying 700 in this case is not going to be a whole lot of fun because it's just pushing everything in the other direction. But picking something right in the middle that is missing is going to be interesting. How do we keep track of the green area when we're eliminating stuff from both sides? Okay, so that's what we'll do next. Okay, we still pick the same thing right in the middle of the entire green area because initially this is all green. Okay, before the first comparison, it is all green because before the first comparison, any element in the array may contain the value 7.1. Without a comparison, I don't know anything about the entire array other than it is sorted. Okay. So out of this entire thing, I should probably update this one too, so it's consistent. Before the first comparison, the entire array is green because we cannot eliminate anything yet at this point. So now we perform one single comparison to the one positionally right in the middle. So we are not talking about median or mode or anything like, well, actually we are talking about median because it's positionally right in the middle, but it's not the mean, it's not the average. Okay, 9 is greater than 7.1. Okay, one single comparison. And just like last time, we can now say, well, everything after this element is also going to be greater than 7.1 because the array is sorted. So we can now say this part is now eliminated, and we only have this much left that can possibly contain the value 7.1. So this part is pretty much the same as the previous example. Out of these 7, row 4 is the one that we'll compare to first. Okay, so we'll compare to this one, and this time we have something a little bit different because 5 is less than 7.1. Using a similar but kind of opposite reasoning, we can now say, oh, if 5 is less than 7.1, then all the elements before this one will also be less than 7.1 because the array is sorted. So now we can say, hey, okay, now we can eliminate these guys as possibilities, but whatever we knew before, we can keep, right? Because if we could eliminate these choices from the previous comparison, these values are not changing. Okay, the array has the same values as last time. So if we could eliminate these choices from the time before, they should still be ruled out this time. Are we doing okay so far with that reasoning? Okay, so we are just adding more salmon or pink color area in this case, and now we have 3 choices left, which is right here. Are we doing okay so far?
Yeah.
Okay, so out of those 3, which are basically on rows 5, 6, and 7, which unfortunately also have the values 5, 6, and 7, which one is the middle? 6 is in the middle. So we compare to the one on row 6. We compare to row 6 only because it is positionally right in the middle. And 6 is less than 7.1. And then we will just use basically the same reasoning and say, okay, everything before this, including itself, we can eliminate. Everything that we have already eliminated remains eliminated. And we only have one choice left. Okay? Just like last time, I cannot conclude at this point because the one element that is green at this point can contain the value 7.1. Okay, so I need one last comparison and basically say 7 is less than 7.1, and at this point we have eliminated everything because the entire column is now eliminated. All right. Are we doing okay so far? Is this, yep, go ahead.
What if we had, like you were saying with the students in Los Angeles district, 30,000 students, how do we find the middle?
It will be about, if you have, let's say it's 30,000.
Right, but the numbers are not 1 to 30,000, it's the student ID numbers.
No, but we only care about the position in the entire array. So it is position 1, position 2, or we should start with position 0, position 1, and then position 30,000 something, right? So you pick the one that is positionally in the middle, not the value. Okay, we're not looking at the value when we pick one to compare to. All right. Any questions about this particular example? Nope. Okay. Do you guys want to do another one? Like one that actually finds something?
Yeah, let's do 5.
Okay.
Let's do 5.
The 9?
Below the 9.
How about 5? It's got a duplicate.
Yeah, but the duplicate is actually not a big deal. Yep.
72.
72? 72 is a little bit too easy. Just by looking at the picture, I already know 72 is going to be easy.
344.
44. 44 is not 344. Okay, 344 is still kind of easy. 75. Okay. 75. Sounds like a lotto, right? Just spewing a bunch of numbers. Yeah, well, we can talk about lotto too if you guys want to. because I want to show you guys whether you really should be investing in that or not. Yeah, yes. Okay, there's one quick and easy way to make that reasoning. Okay, if on the average, it is profitable to play lotto, how can lotto actually make money? Well, there you have it, right? It's just like walking into it's just like walking into a casino, right? The first thing you notice would be, the nice carpet, decor, go to the bathroom, it has got, it's spotless, clean, and got light music playing, right?
Drinks.
So who's paying for that? Well, on the average, is someone going to a casino losing money or making money? But that doesn't stop people, right? Some people say, but I have a, guardian angel, so chances are on my side. I always win. Well, I have nothing to say to those people because I cannot reason with that sort of thing. Well, I wouldn't say it's crazy. It's just not the way I think. So there's nothing I can nothing I can do to to those particular people.
Convince them otherwise.
I hope I didn't offend anyone in this class. All right, so initially the entire thing is green. Before the first comparison, I cannot eliminate anything in this array. I picked the middle one to compare to, which is the one at position 8 in this case, because it's starting from 1 instead of 0. So we established that 9 is less than 75, which means this element and everything before that can be now eliminated. Okay, so we get rid of the first half in this case. And I still highlight the second half with green because now it's really easy to see how the green area changes along with the pink area. Okay, so in the second comparison, I will pick the one in the middle of the green portion that is remaining, which in this case is the one with a value of 72. We compare 72 to 75, and then we establish that 72 is less than 75. Okay, no big deal there. I mean, that's an easy comparison. And as a result, we eliminate the element with the value of 72 and everything before that. Okay, so we go ahead and mark all of that, salmon, and then we have. Now I have to go to Costco and buy salmon. Okay, now we have 3 elements left. 14 is the one in the middle. And you can say, but 75 is right there. How come we are not comparing to 75? Because we have to do it in a very systematic way. Okay, we have to always pick the one in the middle of the green area that is left. Okay, so we pick this one which is right in the middle, and we say, oh, 344 is greater than 75. And as a result, these two are now eliminated because they're all going to be greater than 75. This is the one that is green, and everything else is going to be salmon again. Does that make any sense? Because whatever we could eliminate before this comparison stays eliminated. Okay? The elimination is confirmed. Okay, those things cannot possibly have the value that we're looking for. The green area is unconfirmed. It may contain the value that we're looking for. And that's why the entire thing is about shrinking the green area and growing the pink area. Are we doing okay so far? We are eliminating possibilities here. Okay. Which is also interestingly the name of the game for many board games. But we'll go ahead and finish this one first, and then this is the last one. But you know what? We perform the comparison, and we establish that 75. I want to see if I can get rid of the quote symbol, but it doesn't let me do anything. Maybe a space before that will. Yep, there we go. So we have 75 equal to 75, and we're exiting because we just found the value that we're looking for, and it's the end of this particular algorithm. I'll just do one more trace, but it's not going to take much time. In fact, it will take the least amount of time of everything, because this time I'm looking for the value 9. right? But I do want to show you this case because we are exiting early in this case because we need to figure out how to formulate the condition so that we can also exit early when we have just found the element. Yep, go ahead.
Well, I was just going to ask, if you have duplicates, what we're doing right now, it exits as soon as it finds one.
Yes.
So are we going to talk later at some point about how to find
all the duplicates? Once you find one, if you know the array may contain duplicates, it's pretty easy. You just scan before and after the element that you have located. Because if it is already sorted, the elements with exactly the same value, they have to be contiguous to the one that you have just found. So you scan back, you scan forward, then you will locate all of the ones that have the same value.
But the algorithm would be completely different than that.
No, the binary search algorithm is still the same, except the purpose of the algorithm is just to confirm, is there at least one element with the value that you're looking for? So it will still answer that question correctly. If you want to know how many elements have that value, it's a different question. So you can basically say, okay, after binary search, if I find at least one, now it's time to scan before and after to locate all of the other ones. Okay. All right, so in this case, the entire column is green to begin with, and after one single comparison, we have found the one that we're looking for. So at this point, okay, as far as the algorithm is concerned, it has not eliminated anything. In other words, the entire array can be 9s. Okay, we don't know and we don't care because the algorithm is only caring about is there at least one element with the value 9, and the answer is yes, there is at least one. That's it. It gets its job done correctly. Okay, so now that we have gone through these 4 test cases, we kind of know enough, just knowing how to do it by hand, that we can now start to write the algorithm. And in this class, it's called algorithm design and problem solving. So we're going to design in this case. And as I said many times already, it's really hard to talk about the design process because everybody thinks in a different way. So I can only talk about how I think when I try to come up with an algorithm, and it's always step by step. Okay, it's an approximation of how I think. I cannot describe exactly how I think, how I come up with an algorithm, but this is as close as it can get. All right. So the first thing we want to do is to ask ourselves: is this process repetitive? Are we doing something over and over again? We are. Okay. Now, this is also why in programming it is also important to develop your ability to do abstraction. Does anyone know what does it mean when I say abstraction, or the ability to abstract something, use it as a verb? Finding. Yep. Go ahead.
Is it sort of just to see an example of something and get a general principle out of it, to get like a method out of an example?
Yep, it's also known as generalization. Basically, you're extracting similarities of instances of things that are quote unquote related, or like, or similar. So you're throwing away details and you're retaining only the part that is important. Okay. When applied in some other senses or in other contexts, sometimes that sort of thinking can lead to problems. Okay, I can give you one classic example of using generalization, but in a way that may not be entirely correct. Profiling. Okay, and when you look at how law enforcement people do things, sometimes they use a technique called profiling. It may not be racial. It may not be based on gender, age, and whatnot, but they're using something as a generalization. They're basically saying, okay, in the last 20 arrests that I have personally done, all of these people share a common trait, X. Okay, now that X can be anything. Okay, it can even be how they smell, the criminals. Okay, so the next time they encounter a person on the street or whatever, at a convenience store or whatever, and they smell the same way, that person can say, okay, this has to be criminal, time to arrest. That's abstraction, okay? And we instinctively have the ability to do abstraction at that level. In programming, it's a different type of abstraction because we are looking at how we do things. In other words, we are looking at how we do the trace with sheet 1, 2, 3, and 4, and then we are trying to figure out, okay, what is common to all of these traces? And even within the same trace, what is common to column A, B, C, D, and E? Are we doing something basically the same, except we're applying it to different scenarios, but it's really the same technique applied just differently to different columns? That is abstraction in programming. Okay, it's a very useful skill when you're programming because that's what you're doing. Okay, you know how to solve a problem by hand. You do it many times, and then you ask yourself, okay, but what is the common trait? Okay, how do I express that method so that a computer can do it? Okay, that's abstraction. When we get to subroutines, there's another type of abstraction, but at this point, I just want to point out, what is a useful skill set for, programming. Okay, so we kind of established that we are doing something similar over and over again, which in this case, I'll just say, okay, we have a loop of some kind, and is the loop exiting? In other words, when you look at sheets 1, 2, 3, and 4, am I carrying out the operation indefinitely?
No.
Every single instance, I'm stopping somewhere. Okay, so that means this algorithm probably is going to exit when certain conditions is true. Okay, so going back to our example, when are we exiting? You can describe it in a vague way. It doesn't have to be very specific.
Looks like when either the item is found, when the comparison is equal, or when it's not found in the loop at all.
Okay.
Or when it's not found in the
okay.
list.
So we'll say when the comparison of equality succeeds, right?
Yeah, sure.
It's a lengthy way to say the same thing.
Sure.
Or what is the other one?
Eliminated all the values.
Yeah.
And or okay, we have eliminated all the elements. They are all salmon.
Someone's hungry for lunch, right?
Yeah, now I want to get sashimi.
Ooh.
Yep.
Talk about food.
And this is just the right time to do it too. My evening class is even worse, because people come out from work. It starts at 7 o'clock, and it ends at what, 8:20. Okay, so next thing we want to do is to say, well, is there a better way to say the comparison is succeeding? Okay, what are we comparing? What comparison is succeeding or becoming true?
Well, you're comparing the number we're looking for with like the number that's like what I wrote down as
in the array.
Yeah, in the array, it's basically like the A bar A divided by 2, which is the index of that.
Okay.
Right.
How about we just say an element in the array equals the value, the key that we're looking for. Okay, that's one way to put it. Okay, so that's fine. Not a problem. And in the other description, we can say all elements are eliminated. In other words, they cannot confirm that they are not. They cannot have the value that we're looking for. Okay. Okay, that's good. Okay, now it's time, once we get to an element, the key and stuff like that, we can now start to introduce actual, variable names, because now it's time to kind of make it more specific. So we'll say let variable k be the key, basically the value that we are searching for. We are looking for this value. Let A be the array that we are searching, in which we are searching. In which we're searching. Is that right?
Yeah, sure.
Okay.
Actually, I have a question. Is there any particular reason you don't use like the variable name key and the array name array? You
Just
use
lazy.
It actually gets a little bit confusing for me.
Okay.
Yeah. I was just curious.
Yeah, the key is fine. I mean, if you want to use the word key, that's good too. Okay. All right. So in this case, we can just say loop and loop, exit when. Okay, maybe we don't know what to put inside the square brackets at this point, but we know that equals to key. Okay? It is okay. We are just starting to write the algorithm. It's okay to say, well, we don't quite know what to put inside the square bracket, but the fact that we are dealing with a open square bracket, something close square bracket, means we're referring to an element in the array. Okay, which is good. Okay, that's great because we're saying some element. We don't know which one or how to express the index of that element, but it has to equal to the value that we're looking for. That condition can get us out of the loop. Okay, so we are definitely making this more and more specific. And the other one is basically saying all elements are eliminated, which is, well, I'm going to keep it the way it is, well, the way it was. Because it takes a little bit more work to work this one out. Okay, that's really good. Okay, but at this point, doesn't it mean that whatever is in a question mark has to change?
Yes.
Yeah.
Because if that doesn't change, then if it doesn't equal to the key to begin with, then it will never equal to the key, right? Even if an element does equal to the key, we have to change whatever is in the question mark in order to actually find it and make this comparison successful. Is that making any sense? Okay. So in the next approach, I'm going to say let M be the index of the element that we compare to in an iteration. Okay? Instead of using I, I'm using M in this case, but there's a reason why that is the case. So we'll go ahead and just change the algorithm a little bit and change this to say, oh, instead of question mark, we now have M. Great. Doesn't seem like a whole lot of progress, but it is. Okay, because in the next iteration, or the next revision of this algorithm, we'll start to say, but how are we changing this M for each iteration? This is why binary search is different from linear search. Because in linear search, we start all the way at the beginning, and then we just go on to the next one, the next one, the next one, the next one. But in binary search, we don't really start from the beginning, do we? How do we work out this M here?
Right in the middle.
It's in the middle. Okay. And
Bar A divided by 2?
Yeah.
initially. But for each iteration, M changes all the time. Okay, so let's go back to our spreadsheets here, and I will point out what is M. M is pointing to this thing here. M is not 8. Okay, M is actually 7 in this case because we start counting from 0. But M is pointing to here. 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 So that means for each iteration, we have to recalculate M. Is that making any sense? Okay,
No.
so
Is it M equal to 0.9?
no, M is not the value that we're looking for. That's key. M is the index of the element that we're comparing to. Okay, so that's an important thing to remember. Is we are dealing with the index here. Okay.
M is the row number in this case.
M is the row number in this case. Yep. So I'm going to say, in each iteration, we are recomputing M. Okay, and M is basically the index of the middle element of the green portion, right? Would that be a fair way to describe it? Okay, so we'll describe it that way. So we'll just say that M is the index of the middle element of the green portion. That's good. And all right, so we'll call this just another revision. I think this is a really important addition to the algorithm, because now we're starting to say, hey, this is different from linear search because the way we figure out what other element to compare to in each iteration is different. Okay. But now we are running up against a limitation. Is how do we represent the green portion. Okay, let's go back to the
Those
example.
elements that have not been eliminated?
Right, but how do we keep track of it? In other words,
Oh, I
how
see
do
what
we
you're
represent, the entire thing, and how do we represent almost the first half, almost the first quarter? Okay. Now this one is easy because the beginning part doesn't change. Okay, the starting point doesn't change. But when you look at, I think sheet number 2 is a problem because now the green portion, there are 2 red portions now. Okay, so that means the green portion can be in the middle. The entire green portion can be in the middle of the entire array. Yep.
But do you like set a T off to the side where you transfer the value of how many rows you have over the T?
You cannot because the range can have multiple items, so a single variable is not enough to represent it. Okay.
To represent how many items you have.
You can count how many items and where it starts. Okay, that's one way to do it. Go ahead.
Like you can just get the index of what you last checked, and then you can use that as a reference.
Yep, you can keep track of the index of the first and last element of the range. Okay, it's like bookmarks, right? Because what we have observed here is the green portion is always contiguous. There's only one green portion for every iteration. Is that okay so far? We have never fragmented the green portion. We fragment the pink portion, the salmon portion, but not the green portion. That reminds me of wasabi.
Jack claims we never fragment the pink portion.
Yeah, that's
Someone gets back to breakfast this morning.
Yeah. No, I'm always ready for wasabi and sashimi. Okay. Okay, so what we're gonna do is we'll use that representation. Okay, we want to represent the green area by remembering where it starts and where it ends, because I know it's contiguous. There's only one region. Is that making any sense? Okay. So in this next step here, I'm not going to be able to finish this whole thing, but I'll use B be the index of the first element that has a value, okay, that equals our key, and we'll have another one, E be the index of the last element that equals key.
That allows us to set boundaries
now. That basically that let us remember or be able to represent where is the green area. Okay. Now, given we are using B and E as the indexes of the first and the last element in the green portion, how do we replace this little kind of vague description?
B minus E divided by 2.
Okay, or you can just say B plus E divided by 2.
I'm sorry.
That works too.
B plus E.
Yep. All right. Well, that's handy. Okay, that is really helpful because now we say, if you tell me where the green area is, I know where to find the next element to compare to. The starting, yeah. Okay, and we have 40 seconds left. I can just finish a little bit more. Okay, because today is Thursday. I won't see you guys until next Tuesday, so that means this is kind of important. It's all in the notes already. Okay, the links in Moodle work now, so they're all in the notes, except it's not derived in this way. Okay, the next thing we want to do is to basically say, but what if A bracket M is less than key? Okay, what are we gonna do here? And also, what if A bracket M is greater than key? What do we do in those two cases? So I'm gonna stop here, but I will leave it up to you to think about this first. Okay, think about this, and then read the notes. Okay, the notes. Sorry.
You have to assign anything higher B or close to B.
You have to change B or B as a result of these values. Let me stop the recording.